All right, let's get started. So in the past two meetings, we have been learning a lot about failures, right? And it's lots of theoretical development. So I didn't really get a chance to give you guys any examples. So today, I am going to go through a really big example and trying to cover all the stuff we have learning in early this week and last week, right? It's all about failures. I look at the syllabus. The next exam is in November, right? So about 2 weeks, 2.5 weeks from today. But we have a project 2 coming up, which I'll be giving out your project description on Tuesday, right? It's coming Tuesday. So prepare for that. And we'll be doing the same. So you'll be speaking with your group members, doing the same thing. But the only difference is, remember I said last time? Oh, what's going on? Like I mentioned last time, so this time we are going to do something different in assess individual effort. We are going to have a quiz to assess your learnings in the project, right? So this is about 1/3 of your grade, right? I'm going to give 5 questions related to the project you do, right? So 5 questions related to each of the expectations. So usually we have 5 expectations, right? So you don't have to grade your members anymore, which in my opinion it's not useful and it's a waste of paper anyway, right? So you don't have to do that anymore. The other 1/3 is still from your report. And the rest of the 1/3 is also from your presentation, right? Okay. So any questions about this? No? All right. So we all agree, huh? Well, after all, my main motivation is I'm trying to let everybody learn, trying to keep you guys motivated in learning, not only in classroom but also in the project, right? So the biggest issue the feedback I got from you guys and from the graduate students who took my class while they were undergraduate here, they also say the same thing. So it's no doubt project will learn more, but the biggest problem is for projects, it's only 2 or 3 or some students did the work, right, and the rest of the students get like behind and they didn't really learn much or didn't really contribute much. So that's why we're trying to use a quiz to trying to motivate you guys to learn more. All right. So again, those questions in quiz is really easy as long as you do the project or you get participate in the project. It should be no problem. All right. So it'll be really easy. 15 minutes, 5 questions. All right. But that'll be after all the presentations, after all the discussions of the project. Okay. Any questions?
Will that be like on, like, let's say the first groups that present, are they going to get that quiz that day, or is it going to be?
Yeah. So still be on Tuesday. I'm going to give out the project 2, right? Project 2. So on Thursday, we'll have discussion. So this time, you guys are already familiar with what to do. So it should be really quick. 2 days more than enough, right? So we'll have discussion. And then on the following Thursday, I'll give you 1 week to work on it. Then we'll have a presentations, and then also, of course, another Tuesday for presentations, right? So this is next week. This is also next week, and then the week following, right? So we have presentation part 1 and part 2. This time we're going to start with group 12, right? And then we're going to do the reverse order like we mentioned last time, right? Sorry, group 1, all right? You have to wait. And then on that Thursday, we'll have a 15 minutes of quiz to assess your learning in the project. Right? Make sense? Any questions? You have a question? No? Okay. All right, sure. So let's try it. And again, I am trying to get a better way to motivate you guys to learn. So this is my first time doing this. If you have better feedback or you have better idea, feel free to let me know. All right, I'll take your take your advice if it's a good one. All right. Okay. So, any questions before we start the class today? Any questions? No questions. All right. Okay. Examples. Finally. First of all, let me do a quick review of what we learned in the past week. All we're learning in the past week can be summarized in this plot. You have two-dimensional loadings. Then you have two different failure criteria to assess the failure of the material of the system. We have maximum shear stress, and we have distortion energy. Okay, so the red is distortion energy, and the maximum shear stress is the stuff inside, black. All right. Now, the key point here is maximum shear stress is a little conservative, and distortion energy is a little aggressive compared to maximum shear stress. Right. So we'll see how we can quantify those aggressiveness and conservativeness. Okay, so in this example, we have a hot rolled steel has a yield strength of SYT equals to SYC equal to 100 kilopascal, and ultimate failure strength epsilon F is equal to 0.55. A really high failure strength. It's asked us to determine design safety factor and for the following stress states. A, you have a stress in the x direction that's 70 kilopascal, and stress in the y direction that's also 70 kilopascal, and the shear stress equal to 0, so there's no shear, it's pure tension on both directions. All right, isotropic. All right, so question B. This time your stress gets to 60 kilopascal. In a y direction, becomes 40 kilopascal. And this time you have a shear, which is negative shear stress, 15 kilopascal. All right, C. You have a 0. My handwriting really bad. You guys in the back see it? Good? Okay. Tau xy equal to 45 kilopascal. In case D, we have negative stress in the x minus 40 Pascal. Sigma y is also negative. So this time we have compression and compression on both directions. Oh, the way I write 6 is not good, right? That's what you guys are complaining. Better? 4 is good. 0 is good, right? 6. 7 is good too, right? Great. Okay. Tau xy, this times 15. And okay. Alright, the last one. The last one is my favorite. Sigma 1. Right. Which one is not clear, Diego?
Okay.
Huh?
So
What was the question?
Which one is not clear? What are you guys discussing?
Oh, I was asking about on the problem, the EF of 0.55. What is that?
Epsilon F,
Epsilon F. What is that?
failure strain.
Strain?
Yes.
Okay.
Strain at a failure. Maximum
Oh.
strain it can take before failure.
Okay.
stream.
Okay, so before we start, do you guys like this way better so you can see more stuff?
Yeah.
Yes? Alright, I'll do the way I like. Since I heard yes and no. So. Alright. Okay, so first of all, let's see. Like Diego asked, so therefore I'm going to explain that for him. Epsilon F is failure strain. So when you have a material, you load it up. This is what typically happens. Stress-strain relationship, right? You have linear stage, and then you have a non-linear happening yield after that, and then you have maximum stress, and then failure happens, broken into 2 pieces, right? The strain at a failure is called epsilon F, right? F stands for failure. Okay, all right. Now, why that's important? Remember, all these criteria we learned so far. Therefore, what material? Ductile, right? They are only good for ductile. If it's brittle like glass or ceramic, it doesn't work, right? Okay, so the way we quantify ductile or brittle is by the ultimate failure strain. So the failure strain, if we said it's more than 0.055%, then it's ductile. Or if it's less than 5%, then it's brittle, right? So all these MSDE we learned can be used, okay? Because the ultimate failure strain we have equals to 0.55, which is way higher than 5%. So yes, this checked, right? This is kind of like we have to make sure those rules we learned can be applied to this material, right? So now checked, okay. So we say MSS, the destructive energy applied. All right. Okay, so the question is asking, this problem is asking us to determine this. Design safety factor, right? So design safety factor, in other words, you're trying to look at the maximum stress it allows divided by the stress state you have. right? So we need to know these two quantities. First one is what's maximum strength, what's the maximum stress allowed by using maximum shear stress or distortional energy. Second, where does the stress state lies in, right? So that's something we want to clear off. All right, so keep in mind, we are all looking at this. This is what we need to find. Okay, so for case A, first of all, let me write it here. X is 70 kilopascal. Y is 70 kilopascal. XY is 0 kilopascal. Okay, so relatively speaking, very easy and simple stress state. Let's look at distortion energy first, because relatively speaking, that's easy, right? All distortion energy here is the von Mises stress. Von Mises stress equals to sigma A plus minus sigma A, sigma B plus sigma B square root. All it does is comparing this, right? And once your von Mises stress is above yield strength, then failure is going to happen. That's what we decided, right? Okay, so we plug it in. Sigma A and B, in other words, they are X and Y, right? So just stay here, A, B, and B, right? So in other words, if you set up a coordinate system like this, X and Y, they're the same, right? So sigma A and sigma X are the same. Sigma B and sigma Y are the same. Okay, so plug it in. Right? Okay, and these and these cancel out. Square root and a square cancel out. So this is my answer for von Mises stress using distortional energy. Okay? All right. Now, again, I am looking for this, right? This, how it's determined, design safety factor equal to yield strength divided by my stress state, according to the definition, right? Using distortion energy, that's what you should use. Okay, so SY, in this case, it's given here, let's see. It's equal to 100 kilopascal. All right, 100 kilopascal divided by 70 kilopascal. The answer is 1.43. Right, so design safety factor 1.43. That is my answer. Okay. Any questions so far? All right. Okay, so next. Using maximum shear stress. Okay, maximum shear stress is nothing but just trying to find the maximum shear stress existing, right? So tau max equals to sigma 1 minus sigma 3 divided by 2. Then that is equal to 70 minus 0 divided by 2. Because you have 70, 70, and a 0, right? Because, oh, remember, this is 2D case, right? In this loading. So remember, we still have sigma 1, sigma 3. 1 is your maximum stress. 3 is your minimum stress, right? Don't forget 0. Because if it's 2D case, that's telling you the third direction stress is 0, okay? All right, so 70 minus 0 divided by 2, that is 35 kilopascal. All right, okay. Also, we want to find this. design safety factor. The safety factor, when you use maximum shear stress, it has a parameter of 2 in the denominator. Don't forget that, all right? Two times 35 equal to 100 divided by 70, which is also 1.43. All right, this is my answer using maximum shear stress. Okay, so this is what we did, and like you see over here, you have two different criteria to determine the failure, and we know design safety factor is nothing but just a measure of the failure stress over the stress state you have, right? So when you use maximum shear stress, you are considering the shear stress, while for the distortion energy, you are considering the von Mises stress, which is the same one as what you output from your finite element analysis, right? Okay, so that's that. And yes.
If one is aggressive and one is conservative, how come you still get the same safety factor?
Oh, really good question. Anyone can answer this? Extra, huh?
The same.
What?
Because X and Y are the same.
Yes, because X and Y are the same. Why? Remember, on this plot, we have 6 points, all the same, right? 6 points are the same. So there's a special point over here, right here. What's special about it?
Oh, the DE and MSS are the same, right?
Yes, exactly. The coordinates of this point is what? Right? In the x-axis, it's sy. In the y-axis, it's sy. Right? So if you draw a line to connect them, your stress state for question A is on this line, because this line has angle 45, because this is sy, this is sy. So what you have just now is 70 and 70, right? It's right on this line. So later on, I'm going to tell you why the stress state is on this line. We'll have the same number for maximum shear stress and distortion energy, right? Okay. That's something I was going to say after all the A, B, C, D, E. But I'm glad you brought it up. So just let you know, if your stress state has the same X and the Y, the design safety factor will be the same, right? Okay. And the only thing is, don't forget this parameter, all right? So once you use shear stress, that's how we derived it before, right? Don't forget the denominator has a 2, okay? All right, for question B. Question B is a little interesting. Why? You have X equal to 60 kilopascal, Y equal to 40 kilopascal, and you also have shear stress equal to negative 15 kilopascal. All right, so you not only have tensile, you also have a shear stress. So in other words, in this case, you have all of these, right? Now this is a little confusing. Why? Remember maximum shear stress? What we compared is sigma 1, 2, and a 3. We didn't really consider this, right? So when you have a shear stress in your loading conditions, then the maximum shear stress, you cannot directly use it, because maximum shear stress is based on pure normal stress, okay? And I'm sure you learned this before in mechanics materials. You can do coordinate transformation to get something called principal stress. How many of you remember you learned principal stress? Right. Okay. All right. Sure. It's just a coordinates transformation technique, right? So, the equation goes like this: if you have stressing both normal and transverse, then the principal stress equal to x plus y divided by 2 plus minus square root x minus y divided by 2 square root plus tau xy squared. Alright. Whatever on the right hand side of this equation is the stress state I gave you, right? Okay, so we have stressing x and then stressing y direction, and also we have shear stress. Whatever on the left hand side is my principal stress, is what my maximum shear stress analysis is based on, right? So in other words, principal stress, all it's doing is you have this stress thing, right? We do something called coordinate transformation. Then you transfer the stress to a non-shear stress existing case. All right. Why? Because this stress can be divided into two components, x and y, right? And at the same time, shear stress is nothing but just a stress applied on the x direction. See, this stress and this stress is acting on the x direction and y direction, and they are one pair of stress, and they're calling shear, right? So when you rotate that normal stress to a certain angle, for example theta, then this normal stress actually can be decomposed into x and y, and this x component is holding the same deformation as the shear stress. Okay. All right. But anyway, I'm not going to spend time over there for the principles. If you still remember Moore's circle, you know what principal stress is. Anyway, in this class, we're just going to focus on how you calculate those principal stress. All right. This is the equation you need to remember. All right. Okay. So for case B, what's the question?
Is there a division sign between the left side? Of
The what?
Is there a division sign between the left side of the equation?
Division sign?
Or
Or it's just saying-
sigma 1.
Sigma 1 is your maximum. Sigma 3 is your minimum, right? So, because principal stress in 2D mainly is just on 2 axes. One of them is here, the other one is here. They're 90 degrees apart, right? And the maximum is when the plus is happening. The minimum is when the negative is happening. Because here you have positive and negative, right? Okay. Any other questions? So okay, so this is the equation I'll need to use later on. All right, I'll keep that in mind. what you can do is you plug in the numbers. Let's see, what's the number here? 60, 40, and minus 15. Okay, 60 plus 40 divided by 2 plus minus 60, 40 plus 15. Alright, do the calculation. You'll have two stress. First one is equal to 68 kilopascal, and second one is 32 kilopascal. Alright, so that's my guidelines for both distortion energy and the maximum shear stress. Alright, so once we know the principal stress, distortion energy, again, it's looking at the von Mises stress. Yes? Mm-hmm.
Positive 15, negative?
Doesn't matter.
Oh, because you're squaring.
Here's negative 15, right? So you have a square. Doesn't matter whether it's positive or negative, right? Okay. Either way, you can write positive or negative. They understand. Alright, so distortional energy. So let's plug in those principal stresses. Okay, so this von Mises stress is 59 kilopascal. Again, we're looking for design safety factor equal to SY divided by this, and therefore we have 100 divided by 59, that is 1.7. Okay. Oh, actually, I'm going to show you another way of doing it. Remember, at the end of Tuesday's class, we also introduced von Mises stress calculation, where you have a shear stress, which equal to this, right? Or you have a shear stress component. This is what you can use. Now you can do the same thing, plugging those numbers directly from the given condition. It's going to give you the same von Mises stress as we expected. These two are the same. So in other words, what I'm trying to say is, when you have both normal stress and the shear stress, you try to calculate the von Mises stress using distortion energy, right? You can do two ways. First one, try to find the principal stress, like I did over here, right? Principal stress, find it out, and then plug it in. There's no shear component. Or you can just use this definition. So you have the shear stress over here, plug it in. It's going to give you the same von Mises stress, whichever way you want to do. All right. I'll tell you which way I like to do. I like to do the principal stress. It's because I just like it the harder way, right? It's more complicated. Actually, the reason why I like it is because when you use it for maximum shear stress, you need to calculate it anyway, right? For maximum shear stress, you have to calculate the principal stress. So therefore, even if you did this, then you still have to do the principal stress for maximum shear stress component. So yeah. Anyway, so it's not going to give you any shortcut. All right. For maximum shear stress, what we have is tau max equal to 1 minus 3 divided by 2 equal to 68 minus 0 divided by 2, that is 34 kilopascal. Alright, this n over here is SY divided by 2 times tau max. Alright, so SY is still 100. 2 times 34 is 68. So 100 divided by 68 is 1.47. Alright, so here you compare these two numbers. Alright. Diego, what do you think?
Doesn't look like they're the same.
Huh?
They don't look the same.
The what?
Yeah, it's not the same.
It's not the same, right?
Yeah.
And is that what you expected? Does this answer make sense or not?
What I said is more conservative. Yeah, I think you need less of a safety factor.
Makes sense, right?
Yeah.
Because this number is smaller, therefore it's more conservative, right? Yes.
Is it sigma 1 minus sigma 2?
Which one?
How much?
This one? Yeah. What about it?
Is it sigma 1 minus sigma 2?
Why?
Because you put sigma 68 minus 0.
Sigma 3.
Oh, okay. Yes. Thank you for bringing that up. Then actually, this one is sigma 2. Alright, I apologize for that. Because sigma 1 and the sigma 3 is maximum and minimum. And you have 68, 32, and a 0, which is corresponding to these three numbers, right? So therefore, it's sigma 1 minus sigma 3 should be equal to 68 minus 0. Thank you for bringing that up. I apologize for the confusion. Alright, so this number is smaller, therefore it makes sense because it's more conservative, right? Okay. So question C. Question C, let's see what's the stress state. X is 0, Y is 40 Pascal, and XY is 45 kilopascal. Okay, over here, there's again two ways of doing it, right? You have both normal stress and shear stress. You can calculate the principal stress, do the same thing as what we did in question B, or you can do the other way, like I mentioned. You just calculate the von Mises stress by definition. Okay, so plugging all the numbers, 0 times 40 plus 40 plus 3 times 45 squared in square root. Alright, that is going to give you roughly 87.6 kilopascal for von Mises stress. Okay, and this n equal to xy divided by sigma prime, which is equal to 100 divided by 87.6, which is equal to 1.14 roughly. Alright. Okay, so for maximum shear stress, let's look at something interesting here. This equal to x plus y divided by 2 plus minus square root sigma x minus sigma y divided by 2 square root of out y divided by 2 squared because of that. And what you're going to do is you calculate it now. This is 0 plus 40 divided by 2 plus minus 0 minus 40 divided by 2 plus 45. Okay. Right, go to 20 plus minus. All right, who has a calculator? Who can help me to calculate this out? $69? What about the other?
Negative 29.24.
Yes, all right, thank you. Looks about right. Let's see whether it's right or not.
In this case, sigma 1 has to be 69.24 because we consider it to be the match, right?
Exactly. Because principal stress, I mean, these are two of the, just use two symbols to representing the void, right? For maximum shear stress, what it all care about is maximal minus minimal, okay? So in this case, you have principal stress of 69.24 minus 29.24. You also have 0, right? Of course, this is my 1, this is my 3. Make sense? All right. So tau max equal to 69.24 minus 29.24 divided by 2. All right, let's see what the number is. I think it's supposed to be 49.24 if I'm right. Did I calculate right, Brian? Looks about right. Let's see. Yes, all right. Okay, so when you have that, then the density factor equal to SY divided by 2 tau max, right? Okay, so 100 divided by 2 times 49.24. Wow, it's really close, huh? It's supposed to be equal to 1.02. All right, right on the edge of failure. Okay, so this time, let's see these two numbers, 1.14 and 1.02. Again, this number makes sense because maximum shear stress is more conservative, so it's supposed to give you a smaller number, right? Okay, so any questions so far? No? Okay. Okay, so B. Again, it has compression, and a shear stress. What's the question? So you have negative 40, you have negative 60.
So in this case, why isn't 0 your maximum? In this case, why isn't 0 your maximum?
0 is my maximum, but I still need to calculate the principal stress. Yeah, good question. Actually 0 is my maximum, but I still want to know the minimum. Okay. Minus 60 divided by 2 squared plus 15 squared. Alright, so I have 2 sets of number. Alright, so of course, actually I think I should write it this way, huh? The tau maximum shear stress supposed to be that, right? Then we'll get rid of all the confusions. Yes? Alright, maximum minus minimum. Maximum is 0, minimum is 68. Divide by 2, that's going to give me 34. Okay, alright. Then the design safety factor equal to that 100 divided by 2 times 34, 68. It's also 1.47, which is similar as the answer we got before, huh? Distortional energy. You do the same thing. Looks like this example is making you guys nervous, huh? We'll all go outside. Right. Okay, so 59 kilopascal. How many of you are taking dynamics and assistant dynamics? How was the exam yesterday? So did you guys go to the restroom very often?
Not at all. Before the time.
Huh?
The test.
Alright. Ever is a good teacher, huh?
Not as good as you.
Define good.
Step by step.
Alright, as long as the exam is easy, that's good, right? Alright, so that's the answer. Okay, so the last one is very interesting. Why is that? Because it has the same stress in all directions. Alright, so now the last one, it's very special. The reason is because it has a stress in all 3 directions. Now, once you have that, remember the Vollmeister stress calculation? By definition, if it's 3-dimensional, right, equal to that. So if 1, 2 and 3 are the same, then that's a hydrostatic loading, right? So this formic stress equal to what? 0, right? So that tells you there's no distortion happening here. And we know for distortional energy, it says it's because of the distortional cause failure. So therefore, once you have a 0 in the denominator, then you get infinity, right? Okay, we'll discuss this infinity later in a minute. For maximum shear stress, this tau max equal to maximum minus minimum divided by 2. Okay, so if you have that, that is also 0. And by definition of safety factor, it is also infinity, right? So does it really make sense? Infinity? There's no way you can design something has infinity design safety factor, right? So what does this case E tells us? They do not apply here, right? Because it's against the fundamental of this assumption of this failure criteria, right? There's no distortional energy, so therefore you don't have a distortional deformation, and there's also no minimum and maximum. They're all the same, so therefore you don't have shear stress inside of it, so failure doesn't happen. But theoretically speaking, is it true you have infinity? No, right? Imagine this: if you have a cubic made out of whatever material, for example, made out of plastic. If the 1, 2, and 3 equals to infinity large, of course it's going to cause failure, right? So once we have isostatic loading, that tells you the maximum and the distortional, MSS and the DE, they don't apply, right? So infinity doesn't mean, in physical point of view, it has infinity large design safety factors, right? Okay, so we're done with this example. Took us 1 hour, huh? All right. So we'll be seeing questions like this in exam 2. 5 over them? All right, good. We'll do that. Don't hate me, hate him. All right. So for A, B, C, D, and E, we have Alright, I'm trying to summarize all the design safety factors here, and we can totally draw a conclusion. Right, is that distortional energy is equal or bigger than maximum shear stress, as we expected, because this is more aggressive, this is more conservative, right? Okay, alright, so let's take one step further. Huh? Good. All right. There you go. Now make both sides happy, right? I can write in the bottom. You can look at the front and the top. Okay, so This is our baseline. This is what we learned, right? Maximum shear stress in the center, distortion energy on the outside. Okay, now for this specific case, we know at this point they're all 100 kilopascals because SYC and SYT are the same, right? So they're all 100. So 100 kilopascal on the Y, 100 kilopascal on the X. And over here, you have negative 100. I'm looking at these 4 points, all right? Kilopascal, negative 100 kilopascal. All right. Basically, I took something generic to something specific, right? Okay, so what I'm going to do next is I'm trying to see those design safety factors, how we can describe them on this plot. For case A, it has a load of 70 and 70, right? Remember this? Case A, 70. Let me write it a little better. Sigma X is 70 kilopascal. Sigma Y is 70 kilopascal. And there's no other loading, right? 70 and 70, so probably somewhere over here. So let's say this is 70 and 70. Okay? Alright. Let's draw a line. And like we discussed, this case A is on the line of 45 degrees, right? Okay. Now, what I'm going to say now is, let me define 3 points. Point O, point A, and point A prime. A prime is exactly this point over here. Okay. So I say this design safety factor equal to the length of OA prime divided by the length of OA. Do you believe me? Let's try it. Okay, so OA, we know, should be equal to 100 times square root of 2, right? Because it has 100 on the x-axis, 100 on the y-axis. Right? OA is 100 square root of 2. Agree? Okay. Now, OA prime equal to what? 70 times square root of 2. Right? 70 and square root of 2. Okay, these two cancels out. What is 100 divided by 70? 1.43. Right? Okay. Now, is this accident? It's not, right? Because design safety factor, it is a measure of maximum stress you can apply divided by the stress that you have, right? Okay, so now this might be a coincidence, right? So let's look at other things. For example, let's see, which one should I look at? Let's look at case B, for example. Now B has a stress state kilopascal, 40 kilopascal, and also we have negative 15. And we did calculate the principal stress equals to 68 and 32. This is what we calculated, right? Okay. All right, so 68 and 32 is supposed to be somewhere, let me use a different color this time. 68 and 32 is supposed to be somewhere over here. little lower because the y-axis is only 32. Right? Okay. So if I draw a line over here, I have point on here and here. So this is my point B. This is my point B prime. This is my point B double prime. Now, if you're interested in that, you can do this. This design safety factor caused by maximum shear stress equal to O B prime divided by OB. The distortional energy is N equal to OB double prime divided by the length of OB. Alright. Now, it's a little complicated. If you want to do, first thing of all, you need to determine the theta. So you have slope. Then, therefore, you can form the expression of this line. And then you solve the equations, so you can know what's the coordinates of B prime and B double prime. Right? Plug it back in. So we're not going to do that, but something we can do is qualitative. So tell me which line is longer, the OB prime or OB double prime? Double prime is longer, right? Okay, so that tells you once you have the same denominator, and if the denominator is bigger, of course this number, let's say A, let's say CB, of course A is bigger, right? Let me write it this way. Okay, so let's see whether it's true or not. 1.7, 1.7. Of course, 1.7 is bigger, right? In this case, this is 1.7, 1.47. All right, checked. So, this is example shows you where you have distortion energy and maximum shear stress, how you can relate them to guide your design of materials systems, all right, or other mechanical engineering components. Because once you use these two criteria, you can calculate out what's your design safety factor, or in other words, once I give you a design safety factor, you can compare them whether failure is going to happen or not, right? By comparing them, and that can also guide our design in terms of preventing failure, right? Now again, like I said, distortional energy is fully rely on volumetric stress, which is something you can find from your finite element analysis, right? Okay. All right. For the project 2, we are going to have two-dimensional loading, and then I am going to ask you to use distortion energy to do some CO2 calculation and some finite element calculation, and we'll ask you to compare the results and have some discussion. Yes.
Shouldn't they be switched? You're the B and the A? Shouldn't it be 1.7 B
Oh.
double prime?
Oh, okay.
B squared.
So you mean this, right? Yes? Okay. Sorry about that. Yes. Okay, so basically project 2 will be using all the stuff we have been learning so far and do some calculation with it, right? And I'm going to give you the project description on Tuesday, and we can have some discussion as well, right? I am going to stop here because otherwise it'll take too long to start some new topic, right? Okay, I'll see you guys next week.
Oh yeah. Yeah.
Oh, okay. Another lights. The whole idea of passing is not
No, Stewart. You didn't consider
You can be the one. You know, nobody. I don't know.
When you learn it, it makes sense, and then if you don't use it,
Yeah.
like,
Traffic hours. No, join your team. Right.
Oh, it's because
hey, look at how you're at. Right here, we shake hands like that.
so the whole idea behind it.
How are you striking?
Go in there.
See you